Hi, my name is Madison Matthews, and this is my Physics 2211 Lab 4 report on oscillation. So first to start, I'm going to give a brief introduction. So the purpose of this lab is to investigate the motion of a spring mass system with the mass oscillating in an arc in the xy plane. And we're going to do this using tracker software to track the observed position of the mass, which is a ball on a spring, and then use the GlowScript computational model to show and graph the object's motion and changes in energy. And ultimately what we want to do is determine whether or not the model follows the energy principle, and ultimately it's going to, and we can evaluate if the real system does too based on how closely it matches the model. And we're going to do this using Tracker and GlowScript, as I said before. And here are some fundamental physics concepts that we used in this lab. So first, on the top left side of the equations is all of the information that we can get from Newton's second law, which is saying that the system's change in momentum is proportional to the net force applied. There's also a little free body diagram right there. And then on the bottom left side is all the equations from the energy principle, which states that the system's change in energy is the sum of the work done by the surroundings and thermal energy exchanged with the surroundings. And then on the right hand side are just some various useful equations that we used in our GlowScript code. So in order, there's the velocity update formula, the position update formula, the kinetic energy formula, the gravitational potential energy formula, and the spring potential energy formula. So right here, we're just defining our system as the mass, the spring, and Earth, and our surroundings are nothing because our system is isolated. And this is what the video that we're using looks like. So there's a mass that we call the ball in the code connected to the spring, and then it's moving in a little arc like that. So here's our GlowScript model of our initial conditions. So as I said before, we got a lot of this data from that video. So we have the mass of the ball, and then also our initial ball position vector and velocity vector. And then we have the gravitation constant, the spring constant, which we rearrange the period equation to figure out using the data that we got from the video. And then we used the fact that the net force equals the spring force plus gravitational force to find the relaxed length of the spring. And then over here is the portion of our code adding like the energies down at the bottom after the spring length. And from here, these lines of code just define the energies which feed into the total energy of the system. So we have the kinetic energy, the gravitational potential energy, the spring potential energy, and then the total energy. And I have the equations written out just to make them a little bit easier to see. And then finally, this is the motion loop part of our GlowScript model. So this code is going to define the simulation of the system's motion through energy and momentum principles. So again, I have the equations written out to make them a little bit easier to see. So we have the gravitational force, the spring force, and then the net force, which is just those two added together. And then we used velocity update and position update to update velocity and position. And then down here we have the kinetic energy, the spring potential energy, the gravitational potential energy, and then the total energy again. So here are our results from our GlowScript model. And you can see x position versus time, and then y position versus time, and then the experimental and the computational model on each of these graphs. So the simulated motion data very closely matches the experimental data, which suggests that the system does follow the energy principle. And then the reasons why it might not line up completely perfectly, so some possible sources of error could be due to human error in Tracker, since you have to manually click the center of mass in each frame. And then also in real life, the system is not isolated from the surroundings, so there might be possible forces that we did not account for in our model, like drag. So some what does it mean questions. As I said before, for our model system, the energy principle is satisfied, because as you can see in this graph, the yellow line indicating the total change in energy stays at 0, indicating that no external forces are affecting the isolated system and its energy. And then using the data obtained in Tracker, we can make two separate estimates of the oscillation periods by estimating using the x position data and the y position data. So when we do this with the x position data, we find 1.638 seconds as the period of oscillation, but with the y data we find 1.501. And a lower period of oscillation corresponds with a higher spring constant, so this would lead to two different k values if we were to calculate them this way. Thank you for listening.